So we're here to discuss the chapter 28, the sources of magnetic fields. So we've studied first in chapter 27, the force exerted on the moving charges and a current carrying conductors in a magnetic field. Back then, we did not worry about how the magnetic field got there. We simply took its existence as a given fact. But how are the magnetic fields created, if I may ask? We know that both permanent magnets and electrocurrents in the electromagnets electrocurrents in electromagnets create magnetic fields. So in this chapter, we will study the sources of magnetic field in detail. Okay. We've learned that the charge creates an electric field and that the elect, electric field exerts a force on a charge, but magnetic field also exerts a force only on a moving charge. It is also true that charges creates a magnetic field only when the charge is moving. In a word, yes. Okay. I mean, is it also true that charge create magnetic field only when the charge is moving? Hmm. In a word, yes. Okay. Then our analysis will begin with the magnetic field created by a moving point charge. We can use this analysis to determine the field created by a small segment of a current carrying conductor. Once we do that, we can in principle find the magnetic field produced by any shape of conductor. So then we will introduce the Ampere's law. This is which plays a role in magnetism, analogous to the role of Gauss's law in the electrostatics. Okay, Ampere's law lets us exploit the symmetry and properties in relating magnetic fields in resources. Then you will have your reading assignment, and the moving charged particles within atoms respond to magnetic fields and can also act up as sources of magnetic field. So we'll use these ideas to understand how certain magnetic materials can be used to intensify the magnetic fields, as well as why some materials such as iron act as permanent magnets. Okay, so let's start. So we are looking forward actually here to calculate the magnetic field produced by a single moving charged particle. The straight carrying wire, uh, the okay, and the sorry for the uh, so I checked my pen. So sorry for the interruption. So so a straight carrying wire or a current wire carrying wire bent into a circle. So why wires carrying current in the same direction attract while the wires carrying opposite currents repel. So what Ampere's law is and how to use it to calculate the magnetic field of a symmetric current distribution. How the microscopic currents within the material give them magnetic properties. Okay. So let's go first. Okay. So here is the magnetic field of a moving charge. Okay, so we have here a magnetic field of a moving charge. We'll discuss the magnetic field of a moving charge. So for these fields, points are, so if you have a moving charge, okay, this moving charge will create a magnetic field. For example, we want to calculate the magnetic field uh, at the point P, okay. So the magnetic field is just uh, it's just you can calculate the magnetic field is due to a point charge with constant velocity. For example, at point P with distance r, palihog sa ko there, a distance r, okay. So the magnetic field. So here are the other view behind the charge. If you look at the charge view, so this is the magnetic field. Okay. So if you want to, for example, calculate the magnetic field at point P, so the magnetic field due to a point charge with constant velocity so is equal to the magnetic constant, okay, charge times the velocity cross the unit vector charge towards where the magnetic field is measured. So the distance from point charge, this is r, to where the magnetic field is measured. So you could, if you want to measure here, 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 as long as you know the what we call this one, the distance r. Okay. So here, okay, you can see that yeah, the magnetic field B is just given by, like we said kanina, uh, mu naught I Q V. This is QV cross R hat. R hat, yeah, we call that R hat, okay, as a unit vector. So we don't have this over, okay. So let me write it again. The V is equal to mu naught Q V cross R hat, okay, over 4 pi, okay, over 4 pi over R squared, okay, R squared. Okay, for the magnitude of B, if you want to introduce the magnitude of B is equal to the mu naught I over 4 pi. Then we have the magnitude of the charge Q, V sine phi, okay, over R squared. Okay. So you need to remember the definition of R hat. Okay, R hat is actually a unit vector, which is equal to the vector R over the R. Okay. You need to remember that the magnitude of a unit vector is equal to 1. That's the magnitude of. There's our formula. So, what if, uh, okay, uh, as we discussed, so the unit of B, or the unit of our magnetic field is Tesla, 1T, or Tesla. Okay, we call this one as Tesla. Okay. For the mu naught I, so the value of this mu naught, so this is equal to 4 pi times 10 to the negative 7 Tesla meter per ampere. Okay. So you can also use this relationship where C squared is equal to 1 over E naught over mu naught. So what do we call this constant actually? So the mu naught, that's the constant. Okay. So magnetic constant, we call that one as magnetic constant. So let's have a what we call this one problem where we have two protons move parallel to the x-axis in opposite directions at the same speed v. Okay, we small compared to the speed of light c. At an instant shown, find the electric field and magnetic forces on the upper proton. So this is the lower proton and upper proton, and compare their magnitudes. So we are asked to find the magnetic force and the electric forces. Okay. If you recall, okay, the force due to electric is just equal to 1 over 4 pi E naught uh, Q squared over R squared. That is the electric force due to uh, so that is our uh, we could recall that. However, we have here the magnetic force. So you can hear that this is positive, so the Fe is repulsive. Okay. How about the magnetic force? How do you calculate the magnetic force? Okay. So from the definition, the force, okay, the force V is equal to Q, which is negative V cross V. Okay. So the velocity of the upper proton is this one, negative V. Okay. So actually this is actually or the V is equal to the negative V I hat. Okay. However, you need to find first before you can answer the force. You need to answer find first the what is the this one. What is this B? Okay. Let's change the color. Okay. What is actually this one B? So by formula, this is actually the mu naught over 4 pi, and we have the Q times VI hat. Okay. VI cross J over, okay, R squared. Okay. So because at this point here, if you want to find the magnetic field, okay, so this is actually because here the R hat is just equal to J hat. Okay, because R hat is just equal to J hat. Okay, so here mu naught I over 4 pi. So we have Q times V, okay, times 1. Okay, the magnitude of uh, this is actually V. Then you have uh, I cross K, I cross J, okay, over uh, R squared. Okay. So here, if you recall, uh, this this is I, this is K, this is J. So I cross K, I cross J, okay. I cross J is just positive K. Okay, I cross J is positive K. Okay, so now you can find the what we call this one, the force, which is Q and negative V I hat cross uh, cross B, which is cross uh, mu naught over 4 pi times QV over R squared K, K hat. So we have Q squared. Okay, we have mu naught over 4 pi. Okay, this constant. We have Q squared and then have V squared over R squared. And we have actually I cross K. For I cross K, so in the clockwise, so we have a negative answer is equal to J, negative J, positive J. Negative I, so we have actually negative I or negative I, we have negative I cross K. Okay. If you have this, or if you put this one negative here, okay, and I cross K is just equal to J. So this is equal to mu naught over 4 pi Q squared V squared over R squared, and I cross K is J, then you put the negative J. Okay. So negative is from here, okay, and I cross the J is from I cross K, 4 pi over R squared. If you want to compare this one, so uh, uh, find electric magnetic force upon and compare their magnitudes. So let's compare their magnitudes. Okay. So we have here an FB over FE. So this is actually uh mu naught Q squared V squared over 4 pi R squared over Q squared over 4 pi E naught R squared. Okay, so there will be things will be cancelled in the upper. You have so this one will be surely cancelled. Also the 4 pi, this one and this one. Okay. So mu naught over V squared over 1 over E naught, which is equal to E naught mu naught v squared. That is the ratio of the magnetic and electric force. Okay. So which, if you recall, uh, by this formula, so mu naught E naught v squared, since since mu naught E naught is just equal to 1 over c squared, therefore uh, FB over FB is equal to v squared over c squared. Okay, so that's how to calculate. That's how to calculate. I'm working here, so go to mommy. So, how about the magnetic field of a current element? Don't disturb daddy when working, please. Thank you. How about if you have a magnetic field of a current element? So you have an current element, there's a current on it. What is the magnetic field of this current element with current passing on it with length dl at point P? Okay. So if you want to view it along the axis of current element, so this is the view, and this is its view. Okay. And if you want to find the magnetic field at this point with the distance r, is just equal to the magnetic field due to an infinitesimal current element is mu naught over 4 pi times the current, and we have the dl, the vector length element points in the current direction, cross the unit vector r hat over r squared distance element where where field is measured. Okay. So then the b actually is just equal to the integral of the mu naught over 4 pi. Okay. Uh, integral of I dl cross r hat over r squared. So what do we call this formula? We call this one as the law of Bio and Savart. Okay, the Bio-Savart law. So here, let's try to have an example. For, this is a calculating the magnetic field of a current segment. Okay, so you have a copper wire carries a steady 125 ampere, okay, current to an electroplating tank. So find the magnetic field due to a 1.0 centimeter segment of this wire at a point 1.2 meters away from it. If this point is a point P1, straight out to the side of the segment, and point P2 in the XY plane on a line at 30 degrees to the segment. Okay, so find the magnetic field at these points P1 and P2. Okay, let's try at point P1. Okay, at point P1. So here, the unit vector R hat is just equal to J. So uh, our only in the Y component, KJ. So the unit vector points to Y axis. Okay. So from our formula, if you have a current element, this is equal to the mu naught I, okay, dl cross r hat over 4 pi over r squared. That two. Daddy and okay. Two. So you can see here that dl is pointing actually into what we call this one negative I hat. Okay, pointing to the negative I hat. That's the direction of the dl. Okay, so here we have mu naught over 4 pi. We have we have dl times negative I cross j, okay, because over r squared. Okay. So I cross j is actually k. So we have negative u naught over 4 pi I dl over r squared k hat. So I cross j is, so we factor out the negative here, then left with I cross j, and the answer is just k. Or you can also put this one as mu naught over 4 pi, okay, I dl cross, or you can use the right hand rule. Okay. You can also use the right hand rule. Okay. So if yes, go to mommy now. So you have negative 10. Money too. So we have from our value, so therefore this is equal to, so negative, okay, this one. So negative mu naught. So we have 10 to the negative 7 Tesla meter per ampere. Okay. Times uh so over 4 pi. So is our 4 pi gun. Okay, mu naught over 4 pi. So let's go back here. That's the value of mu naught 4 pi. Okay. So the 4 pi, 4 pi. So this is just equal to 1 times 10 to the this one. Okay, so okay, so and that so mu naught over 4 pi is equal to this one. Okay. So you have the current 125 ampere times the length 1.0 times 10 to times 10 to the negative 2 meters over the distance, which is 1.2 meters squared. Okay, okay. If you do your calculator, the book says that the answer is equal to negative 8.7 times 10 to the this one and k hat. So that is the magnetic field magnitude. Okay. Uh, how about, okay. So let's copy this one first. So how about you're asked to find a point P2. Okay. So let's answer the point P2. So at point P2, so remember that at this point, okay, uh, our r hat now, our r hat now is equal to we have we have we have in negative x and we have in positive y. So meaning and we have an angle here. So meaning so this one is the adjacent. So uh we have actually cosine 30 degrees negative I hat plus sine 30 degrees j hat. So this is the actually the answer. Okay, so therefore our the magnetic field is equal to mu naught I mu naught over 4 pi I dl cross r. Okay, over r squared. So this is equal to mu naught over 4 pi I. So our dl here is along negative j, negative I, dl negative I. So this is cross r hat, which is cosine 30 degrees I hat plus negative negative I hat plus sine 30 degrees. Okay, j hat over, this is over, okay, over r squared. Okay, so So if you use your, what we call this one, right hand rule, okay, negative I cross I, negative I cross negative I, so that would become 0. And negative I cross J, so we have negative I cross J is just what? Negative K. Okay, that would answer. So here, okay, so that for you to follow for pi, uh, we have I dl over r squared. So you have actually this one, negative I uh, cross. Okay, let's factor out this one. Negative I, so we have negative I cross cosine of 30 degrees times negative I plus negative I sine of cross sine of 30 degrees J. Okay. So this one becomes 0, and, and, and and this one here is just sine 30 degrees, or negative sine 30 degrees I cross J. Okay. Or you can put that one, or you can also put this one as sine 30 degrees negative I cross J. So here the answer is here is a negative sine 30 degrees, okay, hat. Here the answer here is sine 30 degrees and negative k hat. So this is basically uh, the same thing. Okay, so here, so you can use the right hand rule. Okay, you can use the right hand rule for this one. Okay, you will eventually arrive at the same thing. So we have mu naught over 4 pi. We have actually uh, I dl cross r squared, and we have a sine 30 degrees negative k hat. Or you can put the negative here, just like what we do here. Okay. So if we plug in the values, so we have negative, so I'll put the negative here, times 10 to the negative 7 d times m over a. Okay, this is the value of the mu naught over 4 pi times 125 ampere times the dl 1.0 times 10 to the negative 2 meters. Okay, times sine of 30 degrees, okay, over the distance 1.2 meter squared, and the direction k hat. This is the magnetic field, and here you can see that this is equal to negative 4.3 times 10 to the negative 8 Tesla. So the meters will be cancelled, the ampere will be cancelled, and we're left with this one, k hat, negative. So this is the direction of the magnetic field, k hat. So points into the page. It points into the page in both cases. So here also in the negative k, okay, it points in the what we call negative into the page. So perpendicular to this plane points into the page. Okay. Now let us find the magnetic field of a straight uh, if we have a straight current carrying conductor. So if we have a straight current carrying conductor, so what would be the what we call this one? What would be the magnetic field? Okay. Okay, so so let's try to answer this one. So this is our what we call this one, the straight current carrying conductor. We will choose a segment DL. Okay, DL in this direction. and this is at point P. This is our dB. So we can see here that uh, using our right hand rule, okay. So R DL, okay, DL cross R, okay, at this point points into the page, okay, plane of the page, into the plane of the page, okay, okay, it points into the page, okay, that's the direction of the magnetic field, okay. So let's try to answer this one. Okay, we know that R squared, and we know that sine of phi is just equal to the sine of uh, theta minus phi. So review your geometry. So meaning this one is just equal to, so the sine of this angle here is equal to the opposite over the hypotenuse, which is R. So which is x over uh, R is equal to x squared plus y squared. So what else? DL again, DL cross R hat. R hat is just shows the direction into plane. So this is equal to this one into the plane, into the page. Okay, that's the direction of our magnetic field. Therefore, from the definition, uh, our let's find first our dB. Okay, it's just equal to, okay, let equal the dB. That is the dB is just equal to mu naught over 4 pi. Then we have I dl cross r hat over r squared. Okay. Then if you integrate that one, we will get p. So if we will integrate that one, okay. Okay. Uh, okay. So this is actually a vector. Okay, if you want to find the magnitude, so magnitude of B is equal to the integral, then mu naught over 4 pi times I, okay, integral of from negative a to a, uh, dl cross r hat, okay, let's, this is over r squared. So if you want to find the magnitude of this, okay, then what will happen is that rb is equal to mu naught I over 4 pi, okay, from negative a to a. So from the definition of the magnitude of this one is equal to the magnitude of dl cross r over r squared. Okay. So dl cross r, okay, the magnitude of that is just equal to dl, the magnitude of the dl times the magnitude of the r hat. This is actually r hat, then sine of phi. So phi is the angle between r and dl and r. So which is equal to dl is actually times the magnitude of r hat is 1 sine of phi. So here dl is just equal to actually dy. So dl is equal to length dy j hat, or dl is just equal to dy. Okay. So so here we have mu naught I over 4 pi integral from negative a to a. So we have dy sine of phi. So this is actually phi over r squared. Okay. So here, so we have mu naught I over 4 pi. Since sine of theta is equal to this one, so we have from negative a to a, so x dy over r. r squared will become r cubed, or r squared times r. Okay, x over r. So this will become mu naught I over 4 pi integral from negative a to a x dy over, we have x squared plus y squared to the 3 halves. So r cubed. So it will become r cubed or x squared plus y squared to the 3 halves. Okay, if you remember, so by using integral, so we have here actually this one. Okay, this one. X dy. So this is actually x dy. So here the x is not x is constant, x squared plus, so so what formula are we going to use? So definitely not this, okay, because this is x dx. Okay, so definitely this is the our formula, and our x would become constant. Okay, so here let's go back here. So the integral from negative a to a of our, so let's put x dy over x squared plus y squared or 3 halves. So this is equal to, so to x times, so here is 1 over dx, so 1 over x squared over, so dy over y square root of x squared plus y squared. So this is actually from negative a to a, integral from negative a to a. So we can cancel this one. Okay. We have y over x. Okay. So we have actually here, uh, 1 over x times negative. So we have a over square root of x squared plus a squared minus uh, negative a over square root of x squared plus a squared. So this is actually equal to 2a over square root of x squared plus a squared, 2a over x, okay, x squared plus y squared. Okay, so therefore our b, so our b is equal to mu naught I over 4 pi. Then we add the integral of this one, x dy, times, which is equal to 2a over x over x squared plus a squared. So that is the integral. Okay. So what will happen then when the length to a of a conductor is very great in comparison to the distance x from point P? So if this length to a is very great, the length to a is very great, we consider it to be infinity long. Okay, if this infinite long, so when a is much larger than x, so what will happen, uh, if, okay, if a is much larger than x, therefore the square root of x squared plus a squared, okay, is approximately equal to a. Hence the limit as hence the limit, okay, the limit as a approaches to infinity, okay, this one will become, okay, mu naught I, if we have the length a is to infinity, where 4 pi over 2a over this a. Okay. So what will happen is it will become mu naught I over 4 pi times 2. So this one will become So cancel, cancel. So cancel, this will become 2. So we have mu naught I over 2 pi. So that is the magnetic field of a, what we call this one, a near a long straight current carrying conductor. So that is the magnetic field. So this is the magnetic field of a near straight current carrying conductor. So magnetic constant equal times current times the 2 pi r. Okay, so we forgot. I guess uh, we, we forgot something. The r. Okay, 2 pi. Actually, this is 2 pi. We still have x here. We still have x. Actually, we still have x here. So we still have x 2 pi x. Okay, that is our x. So physically, situation the physical situation, axial symmetry about the y-axis, hence B must have some magnitude at all points on the circle centered in the current conductor lying in the plane perpendicular to it. So direction B must be everywhere tangent. So such circle in, so ito po yung, this would be the, the magnitude, okay, the magnetic field, it's circling, okay. So therefore, uh, therefore, we can treat this x as equal to r as the distance from the conductor. Okay, for example, this is distance from a conductor. And the distance x may be replaced with r to indicate this is the radius of a circle centered in the conductor. So that's why we can replace x into r. Okay, from here, you become u naught I over 2 pi. Okay, 2 pi r. Okay, you know the direction into the page. Okay. So let's skip this one. And let's go to magnetic field of two wires. If you have two wires, how can you calculate the magnetic field of these two wires? Okay, you have, uh, okay, so please watch figure 28.7a. Okay, maybe we'll include this one. Okay, let's have for this, wait for a second. So let's include that one first. Um, okay, this one. Let's snip this. Okay. Actually, let's also snip this one. So this is how the two wires look. Okay, we'll snip it later if you need. So in figure, end view of the two long wire, straight parallel wires perpendicular to XY plane. So we have two wires perpendicular to XY plane. Each carrying a current but in opposite direction. So this one is out of the page and this one is into the page. Okay. Uh, the points B at points P1 and P2 and P3. So you have P1, P2, and P3. Find the expression of B at any point in the axis of the wire 2. Okay, it's important to snip it again. This one. This one. Okay, this is the direction. So we have that into the page and out of the page. So let's just uh, animate this one. Okay. So here, okay. we are asked to find the find the magnetic field at points P1 and P2 and P3. Okay. So here at P1, so what do you know about P1? So we can find the magnetics B1, B2 due to wires 1, 1, and 2 at each point using the ideas of this section. So then the magnetic field B is equal to B1 and B2. Okay. We use then the equation, the equation the magnetic field is mu naught I over 4 pi times the distance to find the magnitudes B1, B2, this fields, and right hand rule to find the corresponding directions. So B1 shows B1, B2 is equal to B is equal to B total. Okay. So at each point, you should confirm that the direction of the relative magnitudes shown are correct. Uh, uh, and B shows the some magnetic field lines due to this two-wire system. So this is the magnetic field lines in this direction and in this direction. So say for example at point one, so at point one, so we have a magnetic field due to point one, okay, in this direction, and also the magnetic field due to point I, okay, in this direction, B2, okay, okay, and we calculate the B total. Okay, so here, okay, so the magnetic field B total is just equal to the magnetic field B1 plus B2. So we're talking about here at point one, point one. Therefore, so the magnetic field is in the direction negative J in the negative JB1 and the second one is in the what we call this one in the positive J. So we have B1 which is negative mu naught I over 4 pi times the distance here which is equal to 3D. Okay. So here at point one, so let's start at point one. So here the distance from point from wire one from this point is D and this one is D to D. Okay, point two. But this point two, D. Okay, what is this distance here? So this is actually 3D. Okay. So maybe we'll start at point two. Okay. So at P1, point one, we have a distance 2D. Okay. At point one, we have a distance 2D from wire one. Where's wire one? Okay, distance. So this distance here from here is 2D. Okay, that is 2D from wire one. And from wire two is 4D. So meaning from wire two we have 2D. So we have 4D. Okay. 4D. Okay. So so B1, okay. So we have the distance 2D. Okay. So we have actually negative mu naught I. Uh, okay. This is actually 4D. 2D. Okay, 2D. Then in the direction is J hat plus, and the second one is distance 4D from V2 is equal to mu naught I over 4 pi times 2d times 4d j hat. It's this positive, this one is negative. So along this direction, okay, you can also write this one as mu naught I over 4 pi times 2d uh, negative j hat, okay, plus mu naught I over 4 pi times 4d j hat. So this is actually equal to, so this will become to, so so actually this is actually not 2, this is actually 2 pi. So 2, and this is equal to 2. So we have mu naught I over 4 pi d, so negative j hat plus mu naught I over 8 pi 8 pi d, okay, j hat. So if you plus this one, what will happen? So you will have negative mu naught I over 8 pi d j hat. Okay, so that's the magnetic field at point 1. So at point 2, okay, let's copy this one. So let's try to answer the point 2. So at point 2, we have from wire 1 distance d and from wire 2 distance d. Okay. So at point 2, we have the B total. So here at this point 2, the B total is so very big because it's near. So B total, so both is positive. So we have uh, mu naught I over 2 pi, 2 pi times the distance d j hat plus mu naught I over 2 pi d j hat. So the direction will become mu naught I over 2 pi d j hat. Okay. So at point 3, so point 3, so the B total here is equal to the from the wire 1. So we have a distance 1, 2, 3. Actually 3. Okay, 3D. Distance 3D. From here to here is, this one is 3D. Okay, so mu naught I over 2 pi times 3D j hat. This is positive plus the negative distance from this one to this one is just 1D. Just D. So from here up, from here to here to here is just D. Okay. So we have mu naught I, it is negative 2 pi times D over j hat. So if we add this one, so 6, so 1/6 minus 1/2. Okay, so we have uh, 1/3. Okay, so we have negative 1/3 negative mu naught I over pi d j hat. Okay, that is the B total at point 3. So that's how you calculate the magnetic field. Okay. So you can see here that computer cables, just like this one, okay, or cables from audio video equipment create a little no magnetic field, little or no This is because within each cable, closely spaced wires carry current in both directions along the length of a cable. So the magnetic field from these opposing currents cancel each other. That is the reason why there's no magnetic field in the wire. So in this, you use this. this equipment here. So magnetic fields from the opposing currents cancel each other. This is because within each cable, closely spaced wires carry current in both directions along the length of the cable. So uh, usually this opposing currents in opposite directions. Okay. How about uh, calculating force between parallel conductors? So the magnetic field on a lower wire exerts an attractive force on the upper wire. If the wires have currents in opposite directions, they do repel each other. So we have here to find the force. So we have here in direction. Okay, the force. Uh, so how do we find this one? Okay. So figures show segments of two long straight parallel conductors separated by a distance r and carrying currents I and I prime. So in the same direction. Each conductor lies in the magnetic field set up by the other, so each experiences a force. Okay. So each experiences a force. So okay. Let's recall that the force is just equal, so is equal to I prime L and cross B. So we have, for example, so I going to the force is equal where L is the direction of the current I and has magnitude L. So that's the direction. Okay. Since B is perpendicular to the length of the conductor, hence L, so the magnitude of this force is, so this is perpendicular is equal to I L B sine of 90 degrees. So this is equal to I L B I prime L B. So this is equal to mu naught I over 2 pi L 2 pi R. Okay. So because recall B is equal to mu naught I over 2 pi R. So the so we can we can uh the magnetic force per unit length between two long parallel current conductors. Okay, so the force per unit length is just equal to mu naught I over I prime over 2 pi R. So if you have two force between parallel conductors, so that is you can calculate that one. Okay. So the SI definition of ampere is, so 1 ampere is that unvarying current that if present in each of the two parallel conductors of infinite length and 1 meter apart in empty space causes each conductor to experience a force of exactly 2 times 10 to the negative 7 Newton per unit per meter of length. So this definition of ampere is what leads us to choose the value of 4 pi times 10 to the negative 7 Tesla per meter per ampere for the magnetic constant unit. So the SI definition of Coulomb is the amount of charge transferred from 1 second by the current of 1 ampere. Okay, so we will skip this one. Force between parallel wires. So I will leave it on this, it's your assignment. Very easy. So how about we are to calculate the magnetic field of a circular loop? You are asked to How about we are asked to find the magnetic field of a circular loop. Okay. So we wish to calculate, okay. So we wish to calculate the magnetic field on the axis of a circular loop. So how do we answer this one? Circular loop. So what we're going to do is we will uh in this particular case, okay, in this figure, so we will choose our DL, okay. DL, for example, a segment DL in this direction. Uh, so DL cross R is perpendicular. So DL cross R. So this is the direction of our B. Okay. DL cross R are perpendicular. So and the direction of RB caused by this particular LDL lies on the XY plane. So this is our direction of BA. Since so DL cross R, so that's the direction of our B. So because of this one here at point P, so this is the direction. So lies in the XY axis. So using the right hand rule. So here we have R. So let's have R squared is equal to x squared plus a squared. So that is our R. So from the definition, our dB is equal to mu naught I over 4 pi times dl over x squared plus a squared. So why is this? Okay. So let's go back to the definition of the, what we call this one, the magnetic field. Bio-Sabat law. Let's go back to Bio-Sabat law. We have here that dB is equal to uh, mu naught I over 4 pi. We have I dl cross r hat over r squared. Okay. So we have r dl cross r hat over r squared. So what do you mean by this? So this is actually 4 pi. So what do you mean by this actually? So we have dl cross r. So since dl cross r are perpendicular, so uh, dl cross r, okay? So in that direction, uh, perpendicular, so it has actually x and y components. So let me go first to that. Let me go first. So this one. Okay. We wish to calculate the field. So what do we so DL cross R are perpendicular in the figure. Okay. So DL cross R perpendicular to the figure, and the direction of this magnetic field is along this direction. So from the dB, okay, so can we recall what is dB? The definition of dB is equal to mu naught over 4 pi I. No, I'm using it. Find another toy. Later, if I'm done, okay, R squared, that is our dP. So here, since DL and R hat are perpendicular, so this is equal to sine of 90 degrees, which is equal to 1, equal to 1, like sine 90. So, so we have here mu naught over 4 pi, and we have here I, then we have here DL over R squared, which is X squared plus A squared. So that is our dB. Since we have dBx and dBy in angle phi here, okay, we have dBx and dBy, okay, okay. So recall our dB is equal to mu naught I over 4 pi over mu naught I over 4 pi uh, dl over x squared plus a squared. Okay. Since we have dbx and dby, so dbx, so we have mu naught I over 4 pi dl x squared plus a squared cosine of theta. Okay, we have cosine theta. And we have dby, we have mu naught I over 4 pi dl over x squared plus a squared. Okay. Sine of theta. Okay. So what is cosine of theta? Cosine of theta here is just equal to the adjacent, which is a over the hypotenuse, which is equal to uh, r. So r is equal to the square root of x squared plus a squared. So this is equal to the mu naught I over 4 pi dl over x squared plus a squared times a over x squared plus a squared to the 1/2. And we have the mu naught I over 4 pi dl over x squared plus a squared times a over x squared plus a squared the power of 1/2. No, because sine of theta is equal to x over square root of, so this one will become x squared plus a squared. Okay. So next, to find the bx, okay, is equal to the integral of mu naught I dl over 4 pi, and then we multiply this one, this 2 here will become a over x squared plus a squared to the power of 3 halves, because this is actually r squared times r is equal to r cubed. That's why this is equal to 3 halves. Okay. So since this is constant, x is constant, so this is constant, this is also constant, it will not change. Only the dl will change. Okay. So bx is equal to mu naught I over 4 pi dl uh, a over x squared plus a squared to the 3 halves integral of dl. So the dl here, so the integral of dl is just equal to 2 pi a. So the 2 pi times the radius a. So here our bx is just equal to mu naught I over 4 pi, okay, times a over x squared plus a squared to the 3 halves times 2 pi a. So what will happen? So we'll cancel this one, come 2. So we are left, and it will become, so we are left with mu naught I a squared over 2 times x squared plus a squared, the power of 3 halves. So that is our bx. So here, so for example, we get another dl here, dl. So what will happen is that we will have um, another db here, and we have dbx, and we have dby. Okay. So if we have here, so we have also different. So you can see here that the y component will cancel out. Okay, so therefore, uh, the by is equal to 0 because of symmetry. Okay. It will cancel out. So, uh, so the magnetic field along the axis of a loop of radius a, uh, a current, carrying current I is given by the equation below. The direction is given by the right hand rule. So if you have a current, so the right hand rule for the magnetic field produced by a current loop is this one. So this is the current. When the fingers of your right hand curl in the direction of I, your thumb points to the magnetic field. Okay. So the magnetic constant, U naught IA squared, current, and we have the radius of the loop. So the radius of the loop. And we have here x, the distance along x-axis from a point to the loop. Okay, so we derived this one. Already derived this one. Wait, here, we derived this one already. So, what else are we missing? So we also have the magnetic field. What is called of a coil. Okay. So since we have a coil, so the Vx is equal to U naught N IA over 2 x squared plus over Vx. So this N, okay, what do you call? So N is the number of circular loops. Okay. So the minimum value, then the minimum value of the field is, if you want to find the minimum value of the field, so just x is equal to 0. Okay. So if x is equal to 0 at the center, so you can find the minimum value of the field, which is equal to mu naught Ni over 2 times 2a. Okay. So x squared, uh, so that's it. 2a. The minimum value. So meaning, so if your x is equal to 0, so at this point here, so at this point, you can find the magnetic field equal to this one. Okay. You not Ni A. If you have many coils, 2A. Okay. The minimum value at x is equal to 0. So another term is that sometimes you use this one is equal to Ni pi a squared. Sometimes you use that one. So your Bx is equal to mu naught over mu. Okay, in this particular, mu over 2 pi 2 pi x squared plus a squared to the power of 3 times 2. So from this, for a single loop, for 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 a single loop equal to I pi a squared for the single loop. Okay, so that is the magnetic field of a current, circular current loop. Okay. So now let's go to Ampere's law. Okay, special case. So Ampere's law relates the electric current to the line integral around the closed path. Okay. So shown is the special case of a circular closed path centered on a long straight conductor carrying carrying current I out of the page. Okay, so if you have a conductor out of the page, so this is circle here. It is inside the circle of a line integral. And Ampere's law states that B dot dl is equal to mu naught I times I. So let's prove this one. Okay, in simple case, the integral is simple. Okay, so the integral, for example, B dot dl, okay, the closed integral. Okay, so this is equal to, so we have B, so we have B dot dl, so they have the same direction. So we have B dl sine of a cosine of uh 0 degrees, which is equal to B dot uh, B dot dl. So B, we know that B is equal to mu naught I over 2 pi r. So times the dl here, okay? Okay. Dl, okay? So we have here the mu naught I over 2 pi r integral of dl. So dl integral, the closed integral dl here is just equal to the whole circle, which is 2 pi times the radius r. So we have, so therefore the closed integral b dot dl is equal to uh, mu naught I r, mu naught I over 2 pi r times 2 pi r. So, so therefore, we have the result is equal to the mu naught I equals K. So this is the Ampere's law. So if we have what we call, suppose that we have several long straight conductor pass through the surface bounded by the path integral. So thus the line integral of the total magnetic field is proportional to the algebraic sum of the currents. Okay. So just like this one, okay, if for the Ampere's law, we can replace I as I enclosed and the algebraic sum of the currents enclosed or linked by the integration path. So that sum is evaluated by using the right hand rule system. So this one, the right hand rule system, just like this one. Okay. So we have, for example, into the page, current is along into the page. So this is positive and negative I2. If this is out of the page, positive, okay, the current. So meaning this one is into the page and out of the page, the current so will become that one. So in general, the Ampere's law states that the scalar product of the magnetic field and a vector segment of the path is equal to the magnetic constant times the net current enclosed by the path. So, so this is valid even though the path is not of any shape. So if the integral around the closed path is 0, it does not necessarily mean that the magnetic field everywhere along the path, that only that the total current to the area bounded by the path is 0. Okay. So let's have an example. We derive an Ampere's law for the field along straightwise current. So reverse the process and use the Ampere's law to this situation. Okay. So let's skip this one. Okay. So let's go to this one to find the Ampere's law. So what is the use of the Ampere's law? So we have a cylinder conductor of radius r carries a current. So we have here. So this is the, so the current is a uniform distributed over a cross-sectional area of a conductor, find the magnetic field, a function of the distance r from the conductor axis for points both inside and outside the conductor. Okay, so first is uh, we have a cylindrical conductor, radius r. Okay, let's find out find the magnetic field as a function of the distance from r. Okay, okay, inside this what we call this one cylindrical conductor with radius r. So we use the Ampere's law given that uh, before we go to this one, let's note that the J or the uh, current density, current per unit area. So this is current per unit area. So J is just current per unit area is equal to, this is equal to I over K pi R squared. So this is I over the area. Okay, current. So for example, we have here from uh, R is less than R inside. So the enclosed is actually what we call this one, uh, the current density J times the area enclosed, which is pi R squared. So here from this one, so we have I over pi R squared times pi R squared. So cancel this one. So we have actually the enclosed current is just equal to R squared over R squared. Okay. Hence the Ampere's law uh, gives that from the definition of the Ampere's law, uh, B dot dl. So we can see here that B and dl are perpendicular. So this is our in this direction dl. Okay, the same direction as B. So we have B dot uh, BDL. Okay, BDL cosine of 0 or just 1. Okay, so we have B integral of dl. So we have B times 2 pi A is equal to I enclosed mu naught I enclosed. Okay, so here the B is equal to this is 2 pi, actually 2 pi R. Okay, so so this is mu naught over 2 pi R tapos I enclosed. So we know that the enclosed I is equal to this one. So mu naught over 2 pi R times I times R squared over R squared. Okay, cancel this one. So we have mu naught over mu naught I R over 2 pi times R over R squared. So this is the magnetic field inside the conductor. So R is less than R. So that is the magnetic field inside the conductor. So you'll create a line integral encircles the what we call this one, the conductor, and you know that the magnetic field is tangent to that, and you will find the dl. What's the direction of dl? Okay, then you can find the magnetic field at that point. Okay, how about uh when this one? How about in this part at point when R is greater than R. Okay, we know that the I enclosed in this particular is just the whole current I. Okay, the enclosed. So here from the definition, B dot dl is equal to B plus integral of dl is equal to I in B not I enclosed. Okay, so we have B times 2 pi times R is equal to mu naught I enclosed is equal to mu naught I because the enclosed current is I. So your B is equal to mu naught I over 2 pi R. Okay. So here we were able to get the magnetic field of a long cylindrical conductor, okay, outside when R is outside outside the conductor, which is equal to what we calculated earlier about uh, uh, about the magnetic field of a current element. Current element, I mean magnetic field of a straight current carrying conductor. How about this one? A solenoid. Okay. Use Ampere's law to calculate this one. Okay, let's read this one. So, a solenoid consists of a helical winding wire on a cylindrical cylinder, usually a circular in cross section. So, this is we call this one a solenoid. So, uh, you can find the solenoid in figure 28.24. There can be thousands of closely spaced stars, often in several layers, each of which can be regarded as a circular loop. For simplicity, figure 28.22 shows a solenoid with only few turns. So all turns carry the same current I, and the total B field in every point is the vector sum of the fields caused by the individual turns. Okay, but before this one, turns. So the figure shows the field lines of XY and YZ plane. So we draw the line that are uniformly spaced in the center of the solenoid. Exact calculations show that for a long, closely wound solenoid, half of these field lines emerge from the ends of the half leak out through the windings between the center and the end of the figure suggests. So if the solenoid is long in comparison with its cross-sectional diameter, the coils are tightly wound and field inside the solenoid near its midpoint is very nearly uniform over the cross-section and parallel to the axis. The external field near the midpoint is very small. So use Ampere's law to find the field at or near the center of such solenoid if it has n turns per unit length and carries a current. Okay, so this is the magnetic field line produced by the current solenoid for clarity for only few turns. So let's find first what is the solenoid. So this is the you also have toroidal solenoid, but let's just focus on this solenoid thing. So this is the what solenoid looks like. So use Ampere's law to find the field or near. Okay, so we have here 28.23 sketch of this problem. So you have here the segment AB, segment CD, AD, and that one. Okay. Okay. So let's find first the along the side along the side. Let's find first along the side AB. Okay. The side AB B is parallel to the path and is constant. So let's find a path. Okay. So in AB, this is side AB, the magnetic field is parallel to the path. Okay, this is your DL and this is your B, but they're parallel to the path. Okay, so meaning the integral from A to B, the magnetic field that DL is just equal to uh, B times L. So this is length L. So actually, this is actually integral from A to B times DL. Okay, this. Okay, sugod lang kita sa pinakasugod from A to B, B BDL cosine of 0. Okay, so we have here B integral from A to B dl. So the integral, this whole length here is equal to L. So this is equal to B times L. Okay, alongside BC, so we know that BC from BC and DA, the B is perpendicular to the path, and so B, so we know that uh, DL is along that direction and B is in that direction. Therefore, uh, the integral from uh, for example BC B dot DL is equal to integral from BC uh, B DL, which is cosine of 90 degrees, which is equal to 0. Also for the integral of dA, also from dA, B dot DL is equal to 0 because they are perpendicular. For the segment, also around the entire closed path. So along CD also, along CD, we know that the magnetic field is equal to 0. So the B is equal to 0. So around the closed path, then we have, so therefore in the closed path, our what we call this one, in the closed path, so the B dot DL is just equal to BL because the rest is 0. If you add, because if you add this one, the integral of from the closed B dot DL is just equal to from integral from A to B, B dot DL, okay, plus B to C, integral from B to C, B dot DL, which is equal to 0, plus integral of C to D, okay, that is the direction of C to D, C to D, B dot DL, plus integral of uh, D to A, B dot DL. Okay, so this one is 0, 0, 0, and this one is equal to BL. Okay, so the closed integral is just equal to BL. Okay, so in length L, there are NL turns. Okay, so in length L, there are NL turns, which passes once through ABC carrying current wire. So hence, the total current enclosed by the rectangle is, so here, so the total current enclosed is just equal to N times L times this I. That is the total current enclosed. So here, so from this one, so the integral of B dot DL is just equal to BL, okay, which is equal to mu naught N Li. So we can cancel this one. So the magnetic field is equal to mu naught N times the current. So this is the magnetic field of a solenoid. So that's how you use the Ampere's law. So you create a line integral encircling the, what we call this one, integral path. So naka-encircle siya sa umuhang current or sa imong mga wires. Okay? So please read this one carefully. So you have book, you need to read this one carefully. Then I will assign you the, what we call this one, a reading assignment about this chapter here, chapter chapter 28.8 section, magnetic materials. Okay, so about the paramagnetic, diamagnetic, ferromagnetic materials. So probably you will have an essay that for that in your exam. So that's the end of chapter 28. See you in our midterm final examinations. So God bless everyone. Good luck in the exam. If you're a new viewer here in our YouTube channel, please click the like button and click the subscribes button so that you will be able to have more of these lectures, physics lectures that you might be able to use in your lessons, future lessons in physics. Thank you everyone. Thank you for watching and goodbye.